Polar bear. An ice sheet has a rectangular shape with a surface area of 3.5 square meters and 1.25 meters thick. What is the maximum mass of a polar bear that can sit on the ice before sinking? Ice has a density of 900 kilograms per cubic meter. Seawater has a density of 1,025 kilograms per cubic meter. Begin by drawing a free body diagram. They never seem to go away, do they? For the ice sheet. The ice has its own weight downward, that's this term here, and also the weight of the bear on top pushing it down. The buoyant force supports the ice sheet. As long as the forces are balanced, the acceleration is zero. We apply Newton's second law, which is the sum of the forces equals ma. So we have the buoyant force minus the weight of the ice minus the weight of the bear equals ma, but a is equal to 0. So the buoyant force is equal to the mass of the ice plus the mass of the bear times g. In the beginning of this problem-solving techniques, we emphasize that the buoyant force is equal to the density of the fluid times the gravitational acceleration times the volume of the submerged object. In this case, the submerged object is going to be the ice. So the buoyant force, this was from the previous slide, it's equal to the two masses times g, the mass of the ice and the mass of the bear. We replace the buoyant force with this expression, and what do you notice? The g's cancel out, so we're left with a much simpler equation. As we keep on putting heavier bears on the ice sheet, the ice will start sinking, which means the submerged volume will increase until the entire sheet is underwater. And that's the question of the problem. So at that point, we'll consider the ice sunk and the bear is in the water, at least his feet. We then replace V submerged, right up there, that's the equation we got on the previous slide, with the volume of the ice, because that is the maximum submerged volume of the ice. So here's our equation now. We have the rho fluid times V ice, right? We replaced V submerged with V ice. That equals to the mass of the ice and the bear. Rearrange the equation to solve for the bear's mass, whichever bear we're putting on that is finally sunk the ice. Okay, we're getting close, but we're not quite done yet. We've got this expression here. We have the rho of the fluid, the density of the fluid. That's the seawater density, right there. And we can calculate the volume of the ice with the area and height that we're given. We need to substitute, though, for the mass of the ice, right? So rho ice is equal to the mass of the ice over the volume of the ice. So the mass of the ice is rho ice times volume of ice. And that brings us to this equation now. Okay, so there's the ice right there. We take our equation from the previous slide, and to reduce the math, we will factor out the volume of the ice. And then what is the volume of the ice? Well, it's the area times the height. So we now have an expression that gives us the mass of the bear. Any bear more massive than that will push the ice under the water, and we will consider him sunk. So the bear should be lighter than that if he wants to keep floating, or he or she bears. So we put in our rho fluid, and here's our density of the ice. Here's the volume of the ice, and we get the maximum mass of the bear that can sit without sinking the ice is 547 kilograms.